So today's big question is, how have fertilisers and intensive farming changed our world? And the reaction we're looking at in particular today, the Haber process, really changed this area. So first thing I like to do is to do a bit of recall knowledge from our previous lessons and have a look at these examples and decide what would happen to the position of equilibria if these conditions occurred. So as I mentioned, today's lesson is looking at the Haber process and equilibrium. I'm hoping you'll feel more confident predicting the effects of changes in pressure on a system, that you'll be happy applying LCP to the Haber process, and hopefully you'll be happy looking at data and predicting the effects of change in pressure and temperature. First thing I'd like you to do, we've got 9 cards here. I would like you to sort them out into 3 columns. One where the equilibrium shifts to the left, one where it shifts to the right, and a central column where it will make no difference. Pause the video, have a go at these before progressing. So here are the answers, and I'm going to explain in the next slide or two why the temperature ones changed the way they did and why the pressure ones did. So we know from our previous work that increase in temperature favours the endothermic reaction. The endothermic reaction has a positive delta H because it takes in heat energy from the surrounding and has therefore a cooling effect on the system. So if we look at these examples, so we've got A plus 2B, vessels in blur 2C, and the delta H is positive. So if the temperature is decreased, the system is going to want to warm up. So it needs to favour the reaction which will warm up the system. That's the exothermic direction, and in this case that is the backwards reaction. If we look at some of these scenarios where the equilibrium shifted to the right, in the top box we can see we're told that delta H is positive, so that we know the forward reaction, going from left to right, is endothermic. So if the temperature is increased, it's going to favour the endothermic reaction, so it's going to go in the forward direction. Similarly, with the one underneath that in the middle, we've got delta H is positive in the forward direction, temperature increase, it's going to go from left to right. And in the bottom example, we've told that delta H is negative in the forward direction. So if we decrease the temperature, we make it colder, the system's going to want to warm up, and that's going to favour the exothermic direction, so it's going to go in the forward direction. So LCP states that if we increase the pressure, it will favour the side with fewer moles, as long as everything's in a gaseous state. Therefore, if we decrease the pressure, it's going to favour the side with more molecules. So let's have a look at these scenarios. So if we start with those which shift to the left, we can see that the pressure has been decreased, so it's going to favour the side with more molecules. So if we look at the left hand side, we've got 1 mole of P, 1 mole of Q, so we've got 2 moles on that side, and on the right hand side we only have 1 mole of R. So if we decrease the pressure, favour the side with more molecules, it's going to shift to the left. Looking at the ones which stay the same if we change the pressure, top one we've got 1 mole of A, 2 moles of B, so the left hand side has got 3 moles gaseous substances, and the right hand side has got 3 moles, so that's C substance. So if we increase the pressure, it will make no difference because of the equal number of moles on both sides. That's the same for the one below. We've got X plus Y on the left hand side, we've got 2 moles of substances on the left hand side, and we've got 2 moles of Z on the right hand side, same number of moles of each side. The bottom one is slightly different. We can see that one side's got more moles than the other, but you'll notice probably more clearly on your worksheet from class that they are all in the solid state of matter, and changing the pressure only affects those in the gaseous state. Can't compress solids. So if we look at the last one, shift to the right, we've got pressure has been increased, so it's going to favour the side with fewer moles. We've got A plus 2B, so we've got 3 moles on that left hand side, 2 moles on C on the right hand side. The equilibrium shift to the right, goes in the forward direction. So let's make some links to our previous learning and build on that now. So we met the equation nitrogen plus hydrogen goes to ammonia, and obviously it goes in the opposite direction too. So we know that symbol means that the reaction is reversible, and we learnt that when the rate of the forward reaction equals the rate of the reverse reaction, we've said it's met dynamic equilibrium. The energy absorbed in one direction is equal to the energy released in the other direction, and we can see that we've got elements making compounds. So let's have a think about the information given in this symbol equation above, and it's given us a little bit of information about the delta H, the entropy. So is the forward reaction exothermic or endothermic? Will heat in the mixture give an equilibrium mixture with more or less ammonia? Are there more gas molecules of reactants or products? And will raising the pressure give an equilibrium mixture with more or less ammonia? Pause the video, have a go at those. So, forward reaction is exothermic. We know that because it tells us delta H is a negative number. Heat in the mixture will favour the endothermic direction, so we'll favour the reverse reaction, going the left hand side. And there are more gas molecules of reactants, so we've got 3 moles of hydrogen plus 1 mole of nitrogen, we've got 4 on that side, whereas we have 2 moles of ammonia on the other. And raising the pressure will mean there's more ammonia being produced because it will go to the side with fewer molecules, which is in the direction of ammonia to the right hand side. So we talk a lot about shifting equilibria. We can make it move to the left, we can make it move to the right. But why is that important? Why are we concerned about that? Well, it all comes down to the links to industry and actually making the things that we want to make in a timely manner. So the Haber process is the go-to example when looking at equilibria and looking at industrial processes, because it's a really fascinating equation. It involves a lot of compromise, which we'll look at in a minute, but it was also revolutionary. When it was discovered and demonstrated by Fritz Haber and his team in 1909, it changed things historically. And there is lots of interest in reading on this and looking how it affected the war effort, so it's definitely worth researching. But, just to give you a bit of context, we've had the Industrial Revolution. Populations are increasing, we have more and more demand for more food, for example, so we need more fertilisers. And before this process happened, we were doing basically our source of ammonia came from effectively mining, and we call saltpeter or nitra, has different names in different parts of the world, and going through a dry distillation process, or looking at guano, which is basically a big part of the bird poo. And industry could see we are running out of this stuff, we need to find a different method. So when Fritz Haber was able to demonstrate that you could make this stuff with nitrogen, which is in the air, it made a huge difference, and hence it won the Nobel Prize. So why are we interested in ammonia? Ammonia is still one of the largest chemically produced substances in the world. It's used for fertilisers, so we can sustain the food demands for growing population. It's used in nitric acid, it's used in medicines, it's used in explosives, it's used in dye stuff. It has an influence in lots and lots of different areas. So industry now has a chemical reaction they can use to make ammonia, and they're going to want to make this product relatively quickly and affordably. So if we look at this graph, we can see that if we increase the temperature, we're going to make less ammonia. Now we know from previous lessons looking at rate of reaction, one of the things we can do to make things happen quicker is increase temperature, and there seems to be a bit of a clash here with that. Because if we increase the temperature, it's going to favour the endothermic reaction, and so it's going to shift the equilibrium to the left. So, what was industry going to do about this? So we can see that if we want to get the best yields out of the Haber process, we want to do them at a low temperature, because we can see from the previous graph, higher the temperature, the lower the amount of ammonia being produced. But if we did it at a really low temperature, we might get a great yield, and that we get more of the product than the reactants, but it'd be happening really, really slowly. And that's not great when you've got demand and you want to get your products out. So there's a compromise between rate of reaction and the yield in industry. And the compromise is at a fairly high temperature, 450 degrees Celsius. You have to remember that ultimately the aim of the chemical industry is not to make chemicals, it's to make money. So if they can't make their chemicals fast enough, they can't sell them. Hence a compromise. So let's look at what about pressure. Well, we can see here if we increase the pressure, it increases the amount of ammonia. So we know increase the pressure, that's going to favour the side with fewer molecules. We've got 3 moles of hydrogen, 1 mole of nitrogen, so we've got 4 moles of gaseous substance on the left hand side and only 2 on the right hand side, so it goes in the 4 direction. Now industry don't choose to do the reaction at 400 atmospheres, and we've got to ask ourselves, why is that? Well, you need to be thinking about costs and specialist equipment. The atmospheric pressures at 400 atmospheres are ridiculous. Even at 200 atmospheres is extremely high. That we need specialist equipment and we need lots of money to pay the energy cost to maintain those pressures. So another thing that industry is going to utilise is catalysts. So you are expected to know an iron catalyst is used to help speed up the rate of reaction, but it's not affecting the equilibria because it speeds up both the forward and the reverse reaction. What's really crucial is that it provides an alternative route for the energy that has a low activation energy, so we're going to be saving money through lower energy demand. So the key points you need to take home. If we used low temperatures, it would take ages to reach equilibria. It's better to get a 40% yield in 2 minutes than an 80% yield in 2 hours from industry's perspective. If we used very high pressures, the cost of the equipment used increased drastically, and there are also some safety issues. I will warn you now, the exam board are more concerned with you referring to energy and equipment rather than safety issues. And again, we've got this compromise here. It's better to have a 90% conversion at 200 atmospheres than a 95% conversion at 600 atmospheres. There's a huge difference in money. And the great thing about this process, and you will see in some diagrams, is that the unchanged reactants are always recycled. We're not wasting anything here. Any unreacted nitrogen or hydrogen will be pumped back into the system. So this is a common schematic diagram. This one's come from past a QA exam, and it kind of shows we've got the raw materials being input into our reactor, and then nitrogen and hydrogen, and they are being kept in a high temperature, high pressure reactor with some iron there acting as a catalyst. We can see that the gas is produced and then cooled, and the ammonia is distilled off, and then the nitrogen and hydrogen is going back into the reactor that's being used by pipe C. So final task, I want you to think about these questions. First 2 are basically recall ones, so being able to state what LCP is for the first question, and then second question, write the equation for the Haber process, and then state if the forward reaction exo or endo. That should be nice easy recall. Final question is a 5 marker, and it's a kind of question you might see at the end of a paper, which might be worth, in other circumstances, 6 marks, so an extended piece of writing here. Ask you to explain why a temperature of 450 degrees Celsius and a pressure of 200 atmospheres is chosen as compromise conditions, and why iron is used as a catalyst. So you've got to think about, in that question, what are the ideal conditions for this reaction? Why then did they go against those ideal circumstances? So go through temperature. What would be ideal? Why did they choose this temperature? Pressure. What would be ideal? Why did they choose this one? Iron, how does that affect equilibrium, if at all? Why is it used? If you break it down to those sub-questions, you can easily come up with those 5 marks. So, I'm hoping you're feeling happier about the Haber process and equilibrium now. I'm hoping that you're able to state LCP and apply those principles to the Haber process, and that you're also able to understand the compromises industry is making when producing its products and why it's making those choices. Hopefully you've started to interpret data from the graphs we looked at today, but that's something that we can build upon about what if we change the pressure, what if we change the temperature, how does that impact our reaction? I would strongly encourage you to do a bit further dig deep into Fritz Haber. He's a really interesting scientist who had an undoubtedly huge influence on the 20th century. Some would argue positive, some would argue negative, some would argue a bit of both. One of his famous quotes is, "During peacetime the scientist belongs to the world, but during wartime he belongs to his country." And I'm wondering what you think about that. Do you agree with this statement? Do you think he would agree with that statement, having think on the impacts of his developments? Right, thanks for watching.